first one. If a snowball melts so that its surface area decreases at a rate of 4 square centimeters per minute. So when I see this, I'm talking about surface area, and I'm talking about how it changes. If I'm looking at how something is changing, is it regular surface area or is it the derivative? Derivative. So this is the dA dt. I know it's in terms of time because my unit is per minute. If it's decreasing, what should this be? A negative. So you do have to watch your positives and negatives here. Find the rate at which the radius decreases. So if I'm looking for the rate of my radius, that's my dr dt. When the diameter is 39. Okay, if I look at surface area of snowball would be a sphere, right, like a ball. So 4 pi r squared, you're not expected to have that memorized. I would give it to you. There's no mention of diameter here. So when I say the diameter is 39, what's that telling me? Right, just divide that by 2. Okay. So now I can't plug anything in yet because none of these things are constant. The radius is changing, surface area is changing. So we do our derivative. So the derivative of A, we're doing it all in terms of time, so dA dt. Here the 2 comes down, so that's 8 pi r dr dt. So we plug in -4 is 8 pi times 19.5 dr dt. All right. So the -4 equals 56 pi dr dt. One thing I've noticed is when you guys are dividing, make sure you recognize the pi is in the denominator here. So I've found a few times when you divide by pi, your pi somehow flips back up to the top of your fraction. It does stay in the bottom here. So dr dt is -1 over 39 pi. R is my radius, so that was in centimeters. T is my time, so that's in minutes. And it's negative because the radius is getting smaller when our snowball melts. Right. Is that okay? Number 2. The top of the ladder slides down a vertical wall. So we have a wall, the floor, so that would make a right angle. We're going to assume the house is built correctly. The ladder then is here. Now the biggest thing on these problems is recognizing this is the ladder. Does the length of my ladder change? No, so that is going to be a constant. So the top is sliding down at a rate of 0.15 meters per second. So I need a variable for this. What do you guys call it? Y? Okay, so dy dt can be whatever letter you label. Since it's going down, it would be a -0.15. At the moment when the bottom of the ladder is 3 meters from the wall, so I need a label down here. I'll call it x. So when x is 3, it's not always 3. It is sliding away from the wall. So as the top comes down, the bottom is going out at a rate, so that's my dx dt, of 0.2 meters per second. How long is the ladder? So if I call this C, that's what I'm trying to find. Right triangle, Pythagorean theorem, x squared plus y squared equals c squared. When you do the derivative, you get 2x dx dt plus 2y dy dt. But here's where you have to be careful. C is the ladder. What's the derivative of that? All right, so then we plug in. My x is 3, dx dt is 0.2, plus 2y dy dt is -0.15. So then, 2 divided by 0.3, and the y is 4. But is that what I was looking for? No. What I know at this point, that particular instant in time, this is 3 and this is 4. But I'm still looking for my ladder. So now we can do 3 squared plus 4 squared equals c squared. So the ladder is 5 meters long. Okay, we have had several of these ladder type problems where it's really just looking at a triangle that's changing. What questions do you guys have there? The altitude of a triangle is increasing at a rate of 3 centimeters per minute, while the area is increasing at a rate of 4 square centimeters per minute. All right, so I have a triangle. I didn't tell you it was a right triangle. You might have drawn a right. That's totally fine. The altitude is just the height of it. Okay, so I'm just going to call that h. If I know how that's changing, that's my dh dt, or you might have called it a for altitude. Totally fine. It's increasing, so it's a positive 3. The area is increasing 4 square centimeters per minute. At what rate is the base of the triangle changing? So that's the bottom. We want the rate, so I want dB dt. When the altitude is 10, so at the point when my height is 10, and the area is 90. Okay, if I'm talking about area, I need the area formula. What's the area of a triangle? If you called your height A, that's fine. You just have to change your label. Now, what I need to recognize is B and H are both variables here. Neither one is constant, so I can't plug in their values yet. So when I do this derivative, I have to do the product rule. So derivative of the first, derivative of 1/2 B is just 1/2. I did the derivative of B, so it gets a dB dt times the second, plus the first one, derivative of the second. Derivative of H would be dH dt. So dA dt was 4 equals 1/2. My H is 10. I don't know dB dt. Plus 1/2. My base, I didn't give you that. dH dt is 3. Now if I'm trying to find dB dt, I'm going to have to figure out my B right here. How would I do that? How am I going to find my base? Yep. If we go back to this formula, we know that at the instant we're looking, the area was 90. We don't know the base, the height was 10. So at that time, 90 equals 5b, so the base is 18 at that instant. So now if we solve this, subtract our 27, divide by 5, and we get negative 23 over 5. My base was measured in centimeters, my time in minutes. So that's how how the base was changing. At that instant, the base was getting smaller. Is that okay? Number 4. You notice I put a lot of these rates problems on. Doesn't mean like your whole test is going to be rates, but I'm going to give you plenty of practice for them. Big things, you know, draw a picture, label all your stuff. I'm going to give you points just for having all those labels, okay? Doing your derivative. You guys know how to do a derivative, so there's a lot of work that goes into it, but I give points for every step along the way. So even if you get stuck, show as much as you can. Number 4, a balloon is rising at a constant speed of 5 feet per second. So my balloon is floating away. So I'm going to call this y. So if I gave you the rate it's rising, I gave you dy dt. Since it's going up, it's a positive 5. A boy is cycling along a straight road at a speed of 15 feet per second. So he is down here on the ground riding his bike. So I'm going to call that x. His speed, so dx dt, is 15. When he passes under the balloon, it is 45 feet above him. So at the instant when he goes underneath it, my height is 45. But it wants to know how fast is the distance between the boy and the balloon. So that would be this side. So I call that c. How fast is the distance increasing 3 seconds later? Okay, so I am looking for dc dt. But there is a trick to this one. Y was 45 when he was right underneath this balloon. I want my rate 3 seconds after that. So is my y still 45? No. Every second this balloon rises 5 feet. So how high is the balloon now? Right, because it rose for 3 seconds, so 15 feet. So at the point we're interested in, our y is actually 60, not 45. At that time, our x, so we could think when this started, okay, the boy was right underneath it. We know that every second the boy rides 15 feet. So the 3 seconds later, how far has he gone? So at the instant I need my x is 45. All right, right triangle Pythagorean theorem. Are there any constants in this scenario? No, the balloon's going up, the boy is riding away, their distance is constantly increasing. So when I do the derivative, nothing becomes 0. So if we plug in, my x is 45, dx dt is 5, y is 60, dy dt is 5. Equals 2. I don't know c, and dc dt is what I'm trying to find. So how do I find c? So x squared plus y squared equals c squared. Lucky for us, that one is 1 square. That point, the c is 75. So if we work this out, Hold on, I put in 5 for my dx/dt instead of 15, didn't I? That changes things. So we get dc dt to equal 13. C was our height, so that's in feet. T was our time in seconds. So that's increasing 13 feet per second. All right. Questions on these? So you can probably assume there'll be at least one that involves a right triangle. We've had a lot that have Pythagorean theorem. Number 5. A funnel in the shape of an inverted cone. So we have an upside down cone. $30 cm deep. So that's my height. Has a diameter across the top of 20. We know we never need the diameter, we just need our radius. So that means the radius is 10. Liquid is flowing out of the funnel, so it's coming out, at a rate of 12 cubic centimeters per second. Cubic, so I'm talking about what? Volume, so dV dt. Okay, but it's not just 12. What would I have to do? Negative, because it's coming out of my cone. At what rate is the height decreasing? So dh dt. What kind of number should dh dt be? It will be a negative because I've already told you it's decreasing. At the instant when the liquid is 20 centimeters deep, so at the time when our height is 20. Okay, so we know this is the R, this is the H. We've got liquid that's coming down in here. Volume of a cone is 1/3 pi r squared h. If I do this derivative right now, what problem am I going to have? Right. I'll end up with a dv dt, which is fine, a dh dt, which is what I'm looking for, but I'll also have dr dt. And I didn't give you anything to plug in for that. So it would be best if we could get rid of the r. What we have done with these is similar triangles. We know in the entire cone, the height is 30 and the radius is 10. So let's think in general. How are the height and radius related? So if we do similar triangles, the radius is 1/3 the height. So if we plug that in, 1/3 pi I could write as pi over 3. R is 1/3 h squared times h. Okay, I have to square both parts. So 1/3 times 1/3 is 1/9. H squared times h. That's pi over 27 h cubed. Now I'm in good shape. This is what I want to do the derivative of. So derivative of v is dv dt. Okay, if I bring down my 3 over 27 is 1/9, so pi over 9 h squared dh dt. dv dt is negative 12. H was 20. I want dh dt. So 20 squared is 400. You have to divide that over or think of it as multiplying by the reciprocal. So you're going to multiply by 9 over 400 pi. So where's the pi end up? On the bottom. Okay, so if we do that, we should get a negative 27 over 100 pi. H was my height. And then this height was measured in centimeters. T was my time, which was measured in seconds. All right, we've used that similar triangle trick a lot in these volume of a cone problems, so you can probably expect to have one like that on your test, where you have to use similar triangles and get rid of your variable before the derivative. Is that okay? Is this helping, guys? Okay. So all of those problems are really like section 3.9, our related rates problems. This one is 310. The circumference of a sphere was measured to be 90 centimeters, so our C equals 90, with a possible error. So if I'm just talking about error, that's my DC, is 0.5. Use differentials to estimate the maximum error in the calculated volume. So error in volume would be dV. All right, if I'm looking for dV, that means I need a formula with V in it. So what can we say for this one? We have a sphere, so volume of a sphere, 4/3 pi r cubed. All right, when I do this derivative, am I doing these in terms of time? No, this is the differentials. So what do we put when we do the derivative of v? Here, the 4/3 pi, that's just a coefficient, it just stays. So the variable here is r, so the 3 comes down, times 4/3 is just 4 pi r squared, but I did the derivative of r, so it gets dr. Okay, so we're looking for dv, but I don't have r or dr. So how am I going to get my radius and my change in radius? We know circumference is distance around the sphere. How do we get that? That's area. Circumference, distance around the circle is just 2 pi r. Okay, so if my circumference is 90, divided by 2 pi, the radius is 90 over 2, so 45 over pi. So I know that piece. My dr, I'm going to have to do the derivative of this. So the derivative of c would be dc. 2 pi is just my coefficient. Derivative of r would be dr. dc is 0.5 divided by 2 pi. So that's 0.25 over pi, or 1 over 4 pi, either way you want to write it. So now if we clean up, I could cancel like my 4s and my pi's. So really we just have 45 over pi squared, so 45 squared, 2025 over pi squared. You could certainly put that in a calculator and get a decimal, or you can leave it like this. Volume is cubed, so the error in our volume is as much. As a decimal, it's like 205.175. Questions there? Okay. Question number 7. Use linear approximation Okay, this is a fancy way of saying basically write an equation of a line. My a is -2. That's giving me a point. If I put a -2 in for my x, I get the square root of 9, which is 3. So -2, 3 is a point. To write the equation of a line, you need a point and a slope. So my function is the square root of 7 minus x, or it's 7 minus x to the 1/2 power. How do we get the slope? So exponent comes down, inside stays the same, subtract 1 from the power, times derivative of the inside. So that gives me a -1 over 2 radical 7 minus x. Okay, I'm trying to find the slope at the instant when my a is -2. So that means when I'm using -2 for my x. So the square root of 9 is 3 times 2 is 6. So my slope is -1/6. Do you guys use point slope formula or y equals mx plus b? Okay, so my y was 3, and -1/6, x was -2, plus b. So 3, that's like 9 over 3 minus 1 over 3 is 8 over 3. Now, the actual linear approximation then is just this line. If you write y equals mx plus b -1/6 x plus 8/3, that's fine. You'll notice I usually use L of x just to denote the linear approximation. They're the same. I'm not going to count it wrong if you put y instead of L of x. So that's basically just the equation of the tangent line at that particular point. So now I want to approximate the square root of 7.1, so that means we're using this line to approximate 7.1. Now, this one has an extra trick to it that we don't always have. Normally, I would just plug 7.1 in for my x. But notice, the original function was 7 minus x. So that means I need to know, when does 7 minus x equal 7.1? So the x here is actually a -0.1, not a 7.1. And that's because it wasn't, my function wasn't just the square root of x. If my function was the square root of x, you'd plug in 7.1. Since it wasn't, I had to figure out what x was, so that's -0.1.
So why is it written in a
Because that's what we're finding, that's what our function is doing. So we're trying to find the square root of 7.1. You could have also done this way and then squared each side to drop your radical.
I just got confused because I tried to plug a radical 7.1 in
Oh.
for x, and I got really confused.
Uh-huh. Yeah, it's just because that was already included in our function, so our line already accounts for it. Okay, so we're plugging that in for our x, and we get like 2.683. Not a beautiful answer. Obviously, if I'm going to give this to you on the test, I will have to go to great lengths to make sure your numbers are nice, or I would have you like set it up but not solve it all the way or something. Does that make sense? Okay, so another linear approximation. This time we need to find our function. We have something to the 3/4 power, so my function is just x to the 3/4. We need an a value. That's something close to 83 that we could find to the 3/4 power. Keep in mind, a 3/4 means the 4th root of something cubed. What's a number close to 83 that we can do the 4th root of? 81. So my a is 81. The 4th root of 81 is 3 to the 3rd is 27. So there's my point. I need my slope, so I do my derivative. Exponent comes down, x, subtract 1 from the power. So now I need to do 81 to the negative 1/4 power. Okay, that's like 1 over the 4th root of 81. What's the 4th root of 81? So our slope is 1/4. So now we have a point. We have a slope. We're just writing the equation alone. So y equals m times x plus b. Okay. So 27 would be like 108 over 4 minus 81 gives us 27 over 4 to the b. So you could write y equals 1/4 x plus 27 over 4, or linear approximation, don't have to have both, either or. But are we done? No, I asked you to actually approximate this value. So now my x is just the 83. So if I plug that in, okay, that one's actually doable. 83 over 4 plus 27 over 4. That'd be 110 over 4, or 55 over 2, or 27.5.
So that you just linearize it first.
Mhm. Get the equation of your line, and then plug in.
Gotcha.
Is that okay? So that's what you were doing last Friday when you watched the video and I was gone. Then, Tuesday, we did the differentials, which is basically just your derivative. You can write it different ways. The differential just means we're looking for dy. Okay, if you want, you can write your derivative as dy dx and then multiply over the dx at the end. Some of you are just know it goes at the end, which is totally fine. But what we're doing is just derivative like normal. We have a natural log of x plus x squared minus 1 to the 1. Alright, this one's just ugly because I didn't give you a very nice function. The derivative of a natural log is 1 over the argument. But we always have to apply chain rule, so times derivative of the inside. So derivative of x is 1 plus, now I have to do the derivative of this part. So the exponent comes down, inside stays the same, subtract 1 from the power, times derivative of the inside is 2x. Okay, so there's just a lot of chain rule involved here. Not necessarily the differential piece that was hard, just an ugly function. So when I do that, 1/2 times 2, that would cancel. Okay, this is all times 1 plus, you could leave it as x times x squared minus 1 to the negative 1/2. You could, negative 1/2 would move it down underneath, so either way. But the actual differential, all you have to do is tell me dy. So you just essentially multiply that dx over. So it's just your whole derivative times the dx. Basically the change in y is equal to that times the change in x. Is that one okay? So remember, the derivative of a log, 1 over the argument, chain rule as needed. 10. This is back to the 3.7. Remember when we first came back from Christmas and we worked in groups. If I ask you to find marginal cost, what am I asking for? Okay, derivative of 920, that would just be 0, plus derivative of 2x would be 2, minus 0.04x, plus 0.00021x squared. So that part should be okay. Part B, C prime of 100, just means you plug 100 into the derivative you just found, and we're getting a little short on time, so I'm not going to show quite as much. We get 0.1. Does everyone understand where that came from?
Yeah.
Okay, explain its meaning. That's what I really am looking at here. Does this mean my cost is 10 cents to produce 100 items? No. The derivative is how the cost is changing. So when 100 items are produced, the cost is rising because it's a positive, 10 cents per item. Okay, that means if I make one more item, I would expect my cost to go up by 10 cents. Compare that with the cost of producing the 101st item. So what you actually have to do is find the cost of 100 items and the cost of 101 items. Because this doesn't predict the cost, it just predicts how it changes. So I have to know the true cost. So if you went back, the cost of 100 items, plug it into the original function, and you should get 990. When you plug in 101, you get that. So the actual cost increased just slightly over 10 cents. We approximated 10 cents. So we were very close to the increase. All right. Guaranteed to have probably one of these cost problems. Do you know what marginal cost is? Can you explain what the marginal cost is? Can you compare it to the true change? We've also done a lot of the velocity problems, so we'll probably have something related to that. If we have position, how do we get velocity? Derivative. So that's 15 minus 3.72t, so then if you plug in your 2, you get 7.56. That would be meters per second. Part B, what's the maximum height? Think about your height. It went up and it came back down. How do you find this point? So my derivative, 15 minus 3.72t equals 0. And you get a beautiful, 125 over 31? That's the time, but I wanted the height. So if I ask for height, you have to put it into your height function. And that should give you 30.24 meters. What's the velocity of the rock when the height is 25 meters on the way up? So that means your height is 25, so you set your original equation equal to 25. This one did not work out beautifully. You end up doing the quadratic formula. So you have to set it equal to 0. If you do the quadratic formula, you get 2.35 and 5.71. Obviously, not going to do that to you on the test. I'll have something that factors nicely, or I wouldn't ask you this question. Which one of those would be on the way up?
It's equal.
Because it's going up first. Then I want the height, so I plug that into my height function. And when you do that, you get 8.0. Or no, sorry, slipping the wrong one. 6.258. So that's on the way up. Then it asks on the way back down, so how would you find the down? Yeah, plug in 5.71. That one you get a negative velocity because it's coming down. Negative 6.2412. I know I'm not showing everything. Do you guys understand where I'm getting these? Part D, when does the rock hit the ground? If it hits the ground, what's the height? So you're setting the original function equal to 0. And you could take out a t. So if you solve that, you get t equals 0 and 8.06. Which one of those would be when you hit the ground? What's the 0?
When it starts.
It starts on the ground. So it comes back down after 8.06 seconds. How do we find acceleration? So we do the derivative of our velocity function. So our velocity was 15 minus 3.72 t. So the derivative of that is negative 3.72. Units, that's meters per second squared. And what's the velocity at the time when the rock returns to its starting position? When did the rock return to the starting position? So you plug that into your velocity function. And that gives us a negative 14.9. So none of these were exceptionally hard, but I'm really just testing, do you know the difference? How do you get height, velocity, acceleration? How are those things related? And then obviously on the test, we have to have nicer numbers to deal with. Is that one okay? Number 12, a company makes computer chips from square wafers of silicon. Okay, so we've got a square. It wants to keep the side length very close to 15 millimeters and wants to know how the area changes when the side length changes. All right, so it's a square, those are the same. I want that to be close to 15. I want to find a prime of 15. So how do you find the area of a square?
X squared.
Times what? X squared. So the derivative, a prime or dA dx, whatever you want to call it, would just be 2x. So I asked for a prime of 15. So 2 times 15 is 30. And what I'm really looking at here, do you know what this means? So a derivative is how that area is changing. My x was 15, so when the sides are 15 millimeters long, the area, okay, I said that's how it's changing. Is it increasing or decreasing? Increasing. 30 area would be square units, so millimeters squared. So at that point in time, the area is increasing by 30 square millimeters. So really just testing again. Do you understand that a derivative is a rate of change? So if I'm asking for the derivative of A, that's how the area is changing at that particular point in time.